Hello, in this video, you will learn what is gradient descent algorithm and how it is used in linear regression discussed in part 1 of this video. Gradient descent is an optimization method that uses the gradient of the function to find the optimum value, that is minimum or maximum of that function. In linear regression, the parameters m and c are to be optimized such that the mean square error is minimum. This is also called as cost function or loss function. Watch the previous video for knowing the basics of linear regression. The link has been given in the description section of this video. The mean square error function MSE or the cost function J is given by 1 by n sigma I is equal to 1 to n y I cap minus yi whole square. Here, this yi cap is the predicted value and yi is the actual value given in the data set. The predicted value yi cap is given by mxi plus c. This error function should be minimized by choosing optimum values for m and c. To minimize the error, that is, to minimize the function j, find out the derivative of j with respect to m and c. So here j can be written as 1 by n sigma I is equal to 1 to n. In the place of yi cap, you put m xi plus c minus yi whole square. Differentiate this j with respect to m. So dou j by dou m is equal to, let it be dm is equal to 1 by n sigma I is equal to 1 to n 2 into m xi plus c minus yi. So the complete thing is to be taken. And after that, you differentiate this term with respect to m. So you are having only xi for this case. And c is a constant here because we are taking the partial derivative with respect to m. So m is variable, c is constant here. So the derivative of c is 0. Similarly, yi is also 0. So you will get 1 by n sigma I is equal to 1 to n 2 xi into m xi plus c minus yi. Similarly, differentiate j with respect to c. Let it be dc. You will get 1 by n is constant, put as it is. Then sigma I is equal to 1 to n. Then here you put 2 into mxi plus c, and this minus yi will be as it is. Now differentiate this with respect to c. So derivation of this term will be 0, and for c it is 1, and for this yi is also 0. So this will be equal to 1 by n sigma I is equal to 1 to n 2 times m x I plus c minus yi. After finding out the expressions for dm and dc, you can calculate new value for m using m is equal to m minus L into dm. dm is calculated for all xi values using this expression, and it will be put it here. And this L is learning factor. Similarly, you find out the new C value using C is equal to C minus L into DC. After finding out the new values for M and C, you substitute those values here and calculate error. If the error is not very small or zero, use these new M and C values. You put it here and find out dm and dc, and use those dm and dc here. You will get another new value for m and c. Now use those two m and c values, find out the error. If the error is still not satisfactorily minimum, then again you substitute those new MC values here, find out DM and put it here. So this step should be repeated until the cost function J is minimum or very small or zero. If the cost function value is minimum or zero, you take that corresponding new values for M and C and use those values to form the regression line yi is equal to mxi plus c. Now let us summarize this approach. yi cap is equal to mxi plus c. Here xi is the input value and yi cap is the predicted value. First, we have to initialize the values for m and c, and we have to assign a learning factor L. This value will be generally 0.001. It should not be too small or it should not be very large value. If the value is very small, then M and C values will not converge easily. It will take more time. Similarly, if the value of L is very large, then the gradient will be oscillating like this. So it will not converge. So in the third step, calculate the error in the prediction. That means you are taking each data point and yi cap you have to find out from this value, and yi is the actual value given in the data set and the difference is the error. So you find out the error for all the points and take the average. If the average error is 0 or if it has an acceptable minimum value, then the M and C values are optimum values and stop the process. Otherwise, you come to step 4. Here, calculate the average of the gradient of all points for M. That is, you have to compute dm. dm we already found here. So this is the dm. Use this formula and find out dm. Similarly, you find out dc. It is the average gradient for all the points. So after calculating dm and dc, update the m and c. Here this m is the old value already we have, minus this is the learning factor into dm. Similarly for c, it is c minus ldc. So now m and c values have been updated. Go to step 3 and repeat the procedure. In step 3, again we are calculating the error using new M and C values. Calculate the error. If the error is not acceptable or if the error is large, again you update M and C. So the procedure should be repeated until the error you got is acceptable minimum value or if the error is 0. Here we have considered all the data points to calculate as the average of dm and dc. So it is called single batch gradient or simply batch gradient. Since we use all data to decide M and C values, it is greedy approach. All the points are considered as one epoch and the M and C values are updated at the end of the epoch. It can be pictorially shown like this. So this is for batch gradient. In another case, all the data points are single batch or one epoch is divided into mini batches, that is steps. The average gradient is taken for each mini batch and the M and C values are updated for each mini batch or step. Since the gradient values are updated for each mini batch, there will be oscillations in the gradient like this. In the third method, the M and C values or gradients are updated for each data. This method is called as stochastic gradient method. So the learning happens using every data in the data set. So it will lead to more oscillations like this.